Well, I met Claude in 1978 when I became a professor in Paris 13, Paris Nord, Villetaneuse. You had been elected professor just a year before me, I think. And we became very good friends. And we started to run together. Since then, this was 50 years ago, I think we went around the Earth, 40,000 kilometers. And you were mentioning his superpower. I'll give you an example. One time in the Bois de Boulogne, we run. And it takes an hour. And then we take a cafe, because there's a cafe there. And then we go back. And then I meet Claude at Porte Dauphine or something. I stop, open my window, I say, Claude, your wallet is on the roof of your car. So he's the only person I know who can put his wallet on the roof of the car for 1 hour in Bois de Boulogne, not get it stolen, and then drive 5 kilometers without the wallet to fall in the street. Congratulations. Okay, so I'm going to talk to you about climate. This picture shows you that there are at least one industry who is ready to buy your studies is the aerospace industry, because there is a controversy about what is called these clouds behind the airplane, which are called contrail, convective trails. My collaborator, I'm lucky, I am surrounded by super good people. And Pierre-Louis is not here, I don't think so. Didier Smet, Frédéric Echt is here. François, of course, is here, and Claude. So this is the plan. First, I'm going to talk about greenhouse effects. So in various configurations, just taking a greenhouse to grow vegetables first, then compute temperature in the greenhouse, then see what we can do for the climate itself, and complexify the model by introducing polarization and varying refractive index. There are 85 books with the title Radiative Transfer. So it's terrible. It's really terrible. It's all physics, mostly. Not that many simulations. And maybe 3-4 books which have high standard mathematics. By the way, Claude and I, we've been doing a lot of mountaineering. And so in the beginning of the talk, Claude is suffering. Well, seems to suffer. Actually, he doesn't suffer. He was a very strong mountaineer. And even with an overload like this, no problem, right, Claude, in those days. But the atmosphere is cloudy, as you can see. Okay, so what happened is that during pandemics, I lived 3 blocks away from Claude, in a place which people call Hôtel Belfond. So he lives in Château Trudel, I live in Hôtel Belfond. And we were a bit, bored. And so we say, he was writing some report for a Spanish journal. And I told him, why don't we look at climate? It seems to be related. And we started with a book by Fowler, 30 pages, 1 chapter. Terrible. Everything is there, but totally hermetic. So we had to sweat a lot. But in the end, we published the first paper on the topic. And then François stepped in, and he gave, I will tell you. Okay, so we've, mathematicians, by and large, in around 2019 or so, we're a little skeptic about the global warming, because we see a lot of graphics, but we don't see numbers. And when we see numbers, they look strange. Like the 1 degree or 1.5 degree suddenly becomes 4 degrees. It's not the science we're used to. I don't want to, in fact, my talk will tell you that global warming is a fact from this modeling point of view. So what's the modeling point of view? This is a greenhouse, as you can see. This works? Well, anyway, okay. So I'm going to use the pointer. Can you see the pointer? Yeah. So this is a greenhouse. So a greenhouse, how does it work? Well, of course, the greenhouse isolates the cabbage from the wind. And, but there's more to it. And it works also at night, as I'll show you. So the light comes from the sun, and at very high frequency, like this frequency. And so there is absolutely no way you can go to the details and use Maxwell equation. And so you make an assumption that sunlight is a plane wave characterized by a vector which contains E0, a wave vector k, and the frequency. So you count the parameters, E0 has to be orthogonal to k, and you see that you can actually change variables, and you can introduce what is called in physics Stokes vector, which is the first component is the intensity, second is the polarization, and U and V are second polarization, which I will not deal too much with it. And then you can go from one representation to another by this matrix, which is here. Now, when the refractive index is this quantity from the Maxwell equation. When it's not constant, it's better to work with this variable, and then you don't want to work with the Maxwell equation, so you work with what is called a radiative transfer equation, with which, in all its generality, is written here. The problem is that going from Maxwell to radiative transfer equation is as difficult as going from Boltzmann to Navier-Stokes. And there are much less mathematical paper. The only one I know is a paper by Papanicolaou, Rizzik, and Keller, which is 1996, and which is a formal derivation. What you do is you take Maxwell plane waves into a random media, and then you, by doing some asymptotics, you can find this equation here. Okay, so what is this equation? You have a transport term, and you have another interpretation for the radiative transfer. You say light is photons, and photons move along the rays, and the rays are straight if the refractive index is constant and not straight otherwise. So this is a transport term. And then you have an absorption terms. And this last term is not seen in very many papers. There is another paper by some in the Chinese group, which derives this equation from energy budget. And it has this term. This last term is characterized by the torsion of the rays, of the light rays. So when the light ray is straight, this term is not there. And then you have scattering. Scattering is what? At every point, I, the intensity, or the Stokes vector, is characterized by its direction, and at that point. And so scattering is that when a light ray comes into contact with a molecule, it is diffracted into another direction from omega prime to omega. And you have a matrix which goes a scattering matrix. And then you have source here, which in our case will be from the boundary and from the heat inside the atmosphere. Okay, so it's complicated, I understand that. But the complexity is the fact that we are in high dimension, as I explained in my next slide. So we have to simplify it. So first of all, the speed of light is very high, so we can neglect the time dependence. And then mostly the source is from the atmosphere. So the atmosphere is a black body emitting at its own temperature T, according to the Planck function B. And the Planck function is written here. You can rescale it and get rid of all these terrible parameters in front of it. And then you have to couple this equation, because of T appears here, with the equation, the heat equation from the Navier-Stokes equation. And again, you make some simplification. You are interested only in the thermal equilibrium. And then, so this is the equation, convection, diffusion, and the source, which is due to the radiation. And the source is the integral of the first component of this vector. Okay, right? No question? So it's, and of course, the velocity of the wind will be the solution of Navier-Stokes equation. So it's an impossible system in dimension 6, and for every frequency nu, and then on top of that, if you have discontinuities, like in the greenhouse, because of the top, which is made of glass, you'll have Fresnel condition at the jump whenever n jumps. So pretty terrible system. So we have to simplify it. Okay, so the first simplification is to assume that the scattering matrix is isotropic. So then it's characterized by the probability to scatter from one direction to another. Then in that case, you can show that if you have no polarization at the boundary, the polarization is always 0. And so the Stokes vector is reduced to one component. And then if you look at the numbers, this term in the heat equation is in the order of centimeters. So, I mean, the time it takes to go to diffuse the temperature is very large compared to the characteristic time, or characteristic length, rather, of the first equation. So we get rid of this. And so we have one equation for B, a nonlinear equation for B. So linear equation for I, nonlinear equation for B. And it's still difficult. The boundary conditions are standard and connected to the fact that this is a hyperbolic system. But because this equation now for I is simple, we can use the method of characteristics, and we can write a semi-explicit solution of the system here, which I written in terms of an iterative process. So if I know I at some iteration n, I can compute the next one by computing these integrals. So this is called iteration on the source. And basically what I'm doing is these integrals are ray tracing, really. So I'm here in the valley of Chamonix, here. Mouse doesn't work anymore. I'm at a point. I have to look at where is the, for every point on the boundary in the direction omega, I have to see the source of light intensity. And then I have to see from all the points in the atmosphere, the contribution to the scattering. So it's doable. It just will take time, okay? You just have to compute the integrals. And then you have to show that this iteration is convergent. Okay, so further simplification, we go in 1D. In the case of greenhouse, the greenhouse is flat. On top, you have a glass. So there is no dependence in X and Y. There is only dependence on Z. So then you can show that the problem becomes two-dimensional. One dimension is z, the other one is the angle of the ray, but the angle of the ray has only one parameter in that case because of revolution symmetry. It is the cosine of the angle of the ray with the vertical axis, which is called mu. Mu is the cosine of the angle. And so you see, now you have an equation that looks very much, begins to look like the thing that you've studied. You have studied also for radiative transfer in physics applied to, for example, plasma. Except that now I couple with the temperature. And the very big difference is that here, as you will see, the absorption coefficient is, it plays an essential role in what I want to do, meaning I want to see the effect of CO2 in the atmosphere on the temperature. So we have, again, an explicit, a semi-explicit solution, and we can use an iteratron. And the thing is that, and it hasn't been observed before, is that this iteration on the source is actually monotone. No question? So I'm going to apply this to the greenhouse. Now, the greenhouse, the glass on top is a nightmare, is a total nightmare, because I have to write the Fresnel conditions. The Fresnel conditions are very natural for the Maxwell equation. It's just a transmission condition in weak form, let's say. But for the radiative transfer equation, it's a nightmare. It's a jump condition between below and above, written at different points and different angles. So you're welcome to make some sense out of this for the existence of solution. But it's not easy. And on top of that, this coefficient x and y are very nonlinear, as is written here. You don't want to enter into the detail, but it's a nightmare. I had a lot of difficulty to program it, but in the end, here it is. So here's the temperature without the glass on top, and here's the temperature with the glass on top at night, meaning that the temperature comes from Earth, and you see that inside the greenhouse it's a lot hotter. And of course, outside it's cooler, but that's normal. You see, the only source of energy is from the ground, and you put a glass on top, so if you are above the glass, it's cold. And this is a solution, a particular solution for a beam without the glass and with the glass. The glass basically stops the beam, and you have a reflection, which you can see here, and you have, in this case, polarization. Okay, so I'm happy. We can sort of simulate the greenhouse, and you see that it's not easy. So what about the atmosphere? So the atmosphere is a combination of 3 blocks in the climate modeling codes. One is radiative transfer, the other one is meteorology for the atmosphere, and the third one is oceanography for the current. And they're all linked, and unfortunately, the time scale are very, very different. This one is instantaneous. This one is within a week, and this one is within months. And so if you want to couple this, you need a supercomputer, you need a lot of data, and of course, you want to simplify the system, so there's no way you can avoid solving the Navier-Stokes equation, and if you want to simplify, maybe the Intervenant equation here. But here, you'll try to simplify to the maximum. So when I present these results to the climatologists, they say, well, you're doing science that we were doing in the 50s. So I'm not terribly I don't get good feedback from the people. And yet, this is the kind of thing that you've read in newspapers, this picture. So it says that the sun sends light to the Earth, of course, and the Earth gets hot by that. But to get hot for the Earth by sunlight, you need millions of the Earth. And the reason why the physics for a day is not at all due to the fact that the sun heats the Earth. Actually, the sunlight comes to the surface. Some of it is absorbed by the atmosphere, some of it is reflected, and you have a combination of this which is independent from another phenomenon, is that the Earth is a black body which emits in all directions infrared, so this is visible light, and this is infrared radiation. And what they claim is that you have some reflection due to the clouds. And that's all. I mean, that's not science. That's just measurements of energy budgets, right? Because they have these numbers here. And it sort of insinuate that the greenhouse effect is due to the cloud. And that's not true. They know it. And so this picture makes no explanation of the greenhouse effect. And in fact, if you take the most simple model which they use, is to say that the sunlight or the infrared light from the Earth decays with altitude and is a function of the Planck function with respect to frequency, proportional to angles, you see no... so this is how I'm going to take into account the CO2 in the atmosphere. This is a measure from a satellite. It's a Gemini measurement program. The satellite is called, I think it's called Gemini. And what they see at all the frequencies, or wavelengths here, same, they see the intensity of light with respect to wavelengths. And of course, it's highly oscillating because this is an atomic phenomena. You have rays which corresponds to the composition of the atmosphere. And so if you increase the CO2 in two range here, you will have higher absorption. So this is absorption with respect to wavelengths. And so what I'm going to do, I'm going to increase the absorption seen from a high altitude. So kappa is going to change according from black to red. That's the Planck function, and that's the CO2 range with respect to the Planck function. And so if you look at this formula, you say, okay, CO2 actually cools the atmosphere. Bad luck, right? Because K is increased by CO2. So that's no good. Okay, so what I'm going to do, I probably have more slides than I can present, so you stop me. No. It's, this is a birthday party. This is not yeah. Okay, so we wanted to do it first in all its generality. And we did it for the Chamonix Valley because it has high mountain, and here it's out of the question to use the one-dimensional approximation. We use the full 3D. So we wanted to see the effect of clouds. So you have a big clouds across the valley at high altitude, and you have this change due to CO2. And you want to solve these equations in both conditions, okay? And, okay, so just one word about the proof of convergence of this iteration on the source. So this equation, for a simple case of isotropic scattering, you see that this equation is an integral differential equation. It's not easy to analyze, and if you look at it like that, I think perhaps Mercier is the best paper on this, using accretive operator. It's difficult. But if you look at it as a convergence sequence of the iteration of the source, it becomes very easy. Because you have here a linear convection operator with a given source, and then you update, you change in plus 1, in into in plus 1. And why is it monotone? It's very simple. You take two iterations, and you subtract. So you have 0 source at the boundary. You have a source right-hand side, which is this. So if you start from in greater than in plus 1, so if you start from I1 greater than I0, and that's the easiest way to do that is to start from I0 equals 0, and I1 solution of this is positive by construction. So you start from a positive right-hand side, and so at the next level, it's positive. And so you've proved that if you start from 0, it's monotone increasing. You can easily prove also that if you start very high, it's going to be monotone decreasing. So you have two sequences which bound each other, and so you can prove convergence this way. So very easy, right? Okay, so in terms of implementation in 3D, it's very costly. So you have to use the fact that this is almost like a convolution, and we can use a technique which is called H matrices by Hackbush. And this, the technology, Pierre-Louis had the program to do that, and so we integrated in FreeFem, which is our software developed now by Frédéric Echt, and here we go. So this is a solution of a problem which is 7-dimensional, because there are 500 values of the frequency to take all the light rays in account for all the light rays, and this Mont Blanc is somewhere here, Chamonix is here, and the blue is this is at night. So the blue is the snow. We put by hand that at 2,500 there is snow above it, and so in the snow the Earth doesn't emit so much heat, and so we get this result. You get the temperature on the ground and the temperature in a cut vertical to the ground. And basically what you see is that there is a parabolic effect due to the mountains, which is natural. So if you were to do some gliding, hand glider at night in the valley, you should be able to feel that it's hotter in the middle. Good. What about greenhouse effect? So now we do two calculations. One with the Gemini observation, and another one with the modified Gemini to take into account more CO2. So unfortunately, in those days, I did not put enough CO2. So we don't see the difference very much. But you see from the full line to the dotted line, the full line is without CO2, the dotted line is with CO2. So you see that near the ground, it's above, but below, above 6,000 altitude, 6,000, it's below. So and this is a constant. Result that I found through all my calculations, is that this greenhouse effect due to CO2 or other gases, they heat the atmosphere near to the ground, and they cool it above at high altitude. And I talked to climatologists about that, and they know it. There are some papers which publish this, and they say we don't tell too much to the journalists because they don't understand, they will fight back. That's, again, not science. Okay, so what about clouds? So clouds, So by the way, I also did it for nitrous oxide. So the clouds, the same phenomena with clouds, but I have no here. Okay, same phenomena with clouds. I don't have a good comparison with clouds and no clouds here. So, are you still hungry or not? 5 minutes. Good. Now, polarization. So, polarization, it becomes complicated, okay? The book by Pomraning, we have an expert in the room. So, what you do is you take a mixture of isotropic scattering and Rayleigh scattering. So, this is the factor beta. And you can, then I use the one-dimensional approximation. In this case, you have a vector now. But the fact that an important observation is that the right-hand side is always a complex function of z, the altitude, and a very simple function of the angle, polynomial. And the fact that it's polynomial, whenever it's polynomial, whatever I say now works for more complex polynomials, because you can work with moments, sort of moments, and you can convert all this with the moments. So again, same observation. Another observation is that when the sunlight, so the difference is the frequency, sunlight crossing the atmosphere, if you increase CO2, it cools down. Okay? No way you can get a greenhouse effect with visible light. It only with the infrared light. And by the way, this is a nice curve of convergence of the upper lower solution and the upper solution. And you see the complexity because we need a lot of points for the in frequency in order to capture all the complexity of the problem. Okay, so I will finish by saying that with variable refractive index, you have a difficult mathematical problem, because now the linear operator for the transport has characteristics. So n is the refractive index, mu is the angle. So you have two variables, mu and z, and you can compute the characteristics here, and you find that there's a square root. And you don't know which sign to take. So if you can always convert this equation into you can apply the method of characteristics, but you have to choose the sign. And it's pretty terrible to choose the signs because, for example, here is the characteristic line or the ray. The rays for a fancy function, refractive function. You see that you have closed lines. So how am I going to apply the method of characteristic in that case? I'm not going to go around tracing whenever the point meets the initial point. So out of the question. So it's out of the question to use this function. I could possibly do it in this case, but one remark is that whenever the refractive index is not constant, so you can expand it very close to z equals to small z, or I mean small coefficient, you always have rays that, so rays come from the Earth, you always have some that come back. That's a strange thing. Same thing in the other direction. So we had to go to use the finite element method. So this is technical for my audience. I will not go, but finite element methods for a hyperbolic system, normally it blows up. But in this case, it doesn't, because we have this term, kappa, which makes the thing L2 stable. And so we have estimates. We don't have L2 estimates, so it can oscillate, but H1 estimates, but we have L2 estimates. And in fact, the method, the finite element method for this hyperbolic system works very well. You see, in these three cases, no oscillation at all. So this is a final slide. Now I can tell you what is the difference between CO2 and methane, CH4, and nitrous oxide, with or without clouds. And you can see that we still find the general trend that it heats near the ground and cools in the high atmosphere. I do have some oscillation. So you see that this is a polarization which exactly says that the light does not travel in straight line when n is not constant, of course. So these are the data. You don't want to hear about them. But you have a Rayleigh scattering. All the complexity are here. Right, so I'll let you read the conclusion. But finally, Claude has arrived to the summit. This is the same picture set as the first one. In the middle, it was still difficult, but you could see. That's a very good analogy with mathematics. In the beginning, we were in the cloud. At the end, we're happy. Happy birthday, Claude. And now I have I have Bardos in Tibet. No pun. I don't do the pun, but you can guess it. And you have Bardos in Finland, in Lapland. So you're getting closer to Father Christmas, of course. So Claude, happy birthday. Keep to be my lifelong friend. I'm very happy to know you, and I think we had a good time together.